Let's go. Today we'll see today's LeetCode problem. So it's 3620 network recovery pathways. Okay. So today we have a hard problem. So I think this week is entirely focused on graph algorithms and Dijkstra's algorithm. Today we are also going to use Dijkstra. So let's see what the problem statement says. So you are given a directed cyclic graph n nodes 0 to n minus 1. We have given edges array, 2D array, where edges of I represent ui, vi, and cost of I. Okay, let's see this one. So let's keep on highlighting the information then we actually clear about. So we need edges one, we have this one, and then okay. So we have given online. Okay, online means when a node is online or not. So when online of I equals to 4, it means it's not online. So it's just consider it as a analogous to network routing pathways. So when a router or a network node is online or offline, that it simulates that behavior. Okay, next is a path is valid if all nodes are online, right? Obviously, we can go if all gates are open. And the second total cost should not exceed k, right? Every edge, right? Every edge a cost of I. So this one is the cost of I for every node. So if we go from this to this to this and this, right? The total cost should not exceed k, right? X1 plus X2 plus X3, right? The entire should be less than equals to k. This we have to give now. Okay. Now then again, it's for each valid path. There is a score as minimum edge cost along the path. Okay. So let's say for this, if let's say this path is valid from 0 to n minus 1. Okay. So then what is the score for this path is 1 second. Okay, so the score for this part is minimum of x1 comma x2 comma x3. Okay, what we have to do, we have to maximize this minimum. So let's say score 1. So we have to find maximum of score 1, score 2, and so on, score n for all valid paths. Okay, so so let's see the two scenarios we have in this question, right? That defines our approach. First is we have to maximize the minimum. Maximize the minimum. So just think about is whenever there is a question that says maximize the minimum, minimize the maximum or anything, we have to think towards binary search. Okay. Second is we have to find all valid paths, right, whose total cost is less than equals to k. So every node has a cost of I, right? And we have to find paths where, right, sum of cost of I less than equals to k for valid paths. So what is the best algorithm for this? Dijkstra's algorithm, right? So using Dijkstra's algorithm, we always find the minimum path sum from a node 0 to n minus 1. So think of this one. If from 0 to n minus 1, if we are trying to find the minimum, then we can say it can be less than k, and if it's greater than k, there is no other path. Okay. So yeah. So this fixes our approach. We are going to use binary search and Dijkstra's algorithm. Okay. So now how we are going to use the binary search? So binary search means, let's say we have 0 as the, let's say, minimum cost, or you can iterate over the edges of I and find the minimum cost, and you can say what is the maximum limit, right? I equals to what the maximum cost that we have. Okay, so then what we need is first prepare adjacency list. Adjacency list, what it will contain, it is a 2D list, right? So what it will contain, node from I to any node j, what is the cost of it, ci, right? Cij. So how you can do this, you can iterate over you can iterate over this edges of array and prepare adjacency list, and then you push the vi comma ci for any node ui. And since it's a directed graph, so we don't need to push the reverse edges. Okay. Now we have the adjacency list. Okay. And we have the minimum and maximum cost we find. Now we will apply a first binary search. Okay. Let's say while low less than high, right? What it means. Uh, then what we do, we will find the middle element, that is say low plus high. Okay. So we check if it's valid, right? Let's say it's valid. What? Our mid, right? If it's valid, then what do? We go for a maximum score, right? Then we update our low to high plus 1, and we answer equals to mid. Okay. Otherwise, what we do? We just come down high equals to low minus 1, and then what we return. So this is the one binary search, right? So it runs in log of max cost time complexity. Oh, I just hit undo. Okay. Hmm. Oh, good. So it works in log of max time complexity. Now the second step is we have to complete the isValid function. Okay, we have given a mid. So what are we going to do inside isValid? We will use Dijkstra. It is his Dijkstra's algorithm, right? And what we do in the we use main heap for this. See, so the state of the Dijkstra's will be what will be the state, right? What we are going to push to our queue. So let's say we define our PQ equals to say main heap. Okay, what we are going to initial state will be, right? Just say add over. Okay, what do we add in this, right? 0, 0 or initial ones. Okay, now for the Dijkstra's algorithm, we need a distance. Initialize it with infinity initially for all positions. Now next is let's say while the size of our queue, right, greater than 0. So what do? We remove the top element, right? So let's say next node equals to, right, top dot v. So what is the path cost till now? So what are top dot cost? So what is our state? Node comma cost. What is cost is path cost. The total cost that we have till now. Okay, so next. So now first we, right, if we want to traverse this node or not, that depends on if it's online or not. So if online, right, if it's not online of node, right? If it's false, we just continue, right? This node is not online. Next, say let's say okay, then we treat or right, we treat or adjacency list of what node. Okay, for 0 to whatever we have in this right adjacency list. So then we treat over it. So what do? When we iterate over it, we get the next node, right? We get the v comma ci pair. So if, right, our ci, right, if your ci is less than min, right, we will not traverse this, right? Because we are doing a binary search over the cost of I, right? This cost of I, and we are trying to maximize the minimum. Okay. So if our cost is less than the current mid, right, the current cost we are trying to check, we will skip it. Okay. So continue. So next. So now what will be the new cost, new path cost? New path cost equals to, right, the ci, the cost of this one plus the total cost that we have till now, right, that we get here path cost. Now see, if this new path cost, right, is less than k, right, then only we call, right? See, if it's greater than k, we don't want this path because then it's invalid. Okay, so and then we check if distance of what the current node, right, distance of v from here, if it's already greater than new path cost, right? If it's greater, what does that mean? It means, right, the new path that we found is better. So we update the distance. So we obtain distance of v equals to new path cost and we add it to the priority queue. Priority queue dot add what is v is our node and this is our new path cost. Okay, now we have to add the base case. We return false if we don't found it, and right when we pop this one, right here, if we check if this node equals to n minus 1, we return true. Okay, so we got the algorithm, right? So that's the question. We solve it in two parts. We first do a binary search over, right, all cost values, right, between low comma high. Okay, the next is valid function. Is valid function is basically what, returning a Dijkstra's algorithm to check if we can reach to the n minus 1 with total less than equals to k. Okay, so yeah, let's go and check the implementation of. We are going to solve this question in Java. Yeah, I'm new to Java, so let's see if I can code this one or not. what do we need first? We have given long k, so path sum can be greater than equals to k. So what do? We initially get and n equals to online dot right length. We need to prepare the adjacency list, right? Which a list of list, and we need a pair, right? Adjacency list equals to new array list we used to do, and we have to initialize it 0 a less than right and I plus adjacency list dot what and right. We add a new array list, empty array list for each position. Okay, then we have to initialize the pair as well, right? So what do? We do class pair, right? So what will our parent have the next and what it of cost, right? Then we do pair tv comma tc. This is the default constructor for this one. And now this dot v equals to what b and this dot c equals to c. Okay. Now we will fill our adjacency list. We do for int, right? We iterate over each edge of edges. So we have right next the u equals to edges of 0, v equals to edges of 1, c equals to edges of 2. So next is we are going to add it to the adjacency list. Adjacency list dot get u. For u, we need to add what? V comma c. So we'll do a new pair. We do v c. So we add it to the adjacency list. What do we have now? So while we add it to the adjacency list, we calculate our low and high for the binary search. So let's say let's keep it long basically, huh? Long, long, low. Just one we can say. What do we say? We need right the let's allow 0 and high equals to 0 and we'll update the high here. High equals to math dot what? Math dot maximum high comma what? And we need to convert c to long basically, I think. C it's one long. Yeah. So once we have this one, we do a binary search. Let's say long, right? So we can say int answer equals to -1, while low less than high. And this value can be actually end, right? High and low. So we don't need this conversion here then. Okay. So we found int mid equals to low plus high, right? We do embed. So now next is if we check if this valid, right? If our mid is valid, we along with this pass we adjacency list, we pass our online, we pass k. If it's valid, then what do? We check for the next higher, right? So we do low equals to mid plus 1 and we update our answer. Right answer equals to mid. If it's not, we do high equals to mid minus when we check for its lower value. Okay. Then we return the answer. This is our binary search. Now we have to complete the is valid function. Huh? So let's see. Private, it will return a boolean value, either true or false. Is valid. So int right the mid, right? Then list of pair. This is our adjacency list. We have boolean online, then we have int k, right? So we long k. Path sum can be greater than, right? So now what we have to do is valid. What we are going to write, we are going to apply Dijkstra's algorithm here. So what do we do for Dijkstra's algorithm? We first define the distance array. Long distance equals to what? New long. We fill it with the maximum value arrays dot fill. What can be the, so let's say I'll say something just big value. Let's, and we also need state pair, right? We also need state pair for Dijkstra's algorithm. So we do class state, right? What will be the state? This is our, this will be our node. Next will be long path cost, right? Path cost is the path cost that we have till now. And with our state, we have empty node, long, we have path cost. We are going to update it node equals to, right? This dot node, right? This dot node equals to node, we do this dot path cost equals to path cost. We update it and we define a big value. It's a very big value, they say it. private, we say long, we say infinite equals to what do we say? Right, I think this is fine. If not fine, we'll check it later. So just keep correct me if I write something wrong in Java. So distance, and we do infinite, we initially initialize it, we have to initialize our priority queue. Priority queue will consist of pair. So priority queue equals to new priority queue, and then we have to add a compare, I think, AB, right? So what this will be a min heap. So what do we compare, right? We compare A dot path cost minus. So we can say here integer dot compare, integer dot. I think that these are long, no? So sorry. So this me. So what do we do? We have to compare this one, huh? Long dot compare this one. A dot path cost comma B dot path cost. We compare both of these. Now once we have a priority queue, we initially need to add the, we can do add or offer both, new pair and new state. So we have to use state here as well. We have to initialize new state, right? What is 0? Initially everything is 0. Okay, then we do distance of 0 equals to 0. We'll update the distance for distance, right? Next is we have to do is while priority queue dot size, right? This is greater than 0. Then what do? We remove the top element, right? We do pq dot remove. So what will be the current, right? And the current equals to tom dot node long path, right? Path cost equals to what? Tom dot path cost. Now if current equals to n minus 1, right? N minus 1 is what? Online dot size. We have to get n. Okay, we have to get n before this, right? We need to initialize this as well. And n equals to online dot length, and then we update it. We make length n. If it's n, we are going to return true. It means it's valid, right? And we check if not of online of what. Otherwise, if our current road is not online, we'll just continue. Then we are going to iterate over the list pair, list state, right? List pair, sorry. List pair, right? List pair, say A. We have to get adjacency list dot get what we need to get for the current. We are going to do it, right? So once we have, we can say what will is the next node. Next node is A dot. What have we defined there? So we define this node V or C. We have defined V comma C. So we have A dot V basically. And the cost equals to A dot C. The next is what we have to do. Next we have to check if this cost, right? If this cost is less than med. If it's less than med, we don't want this, right? We'll skip it. Otherwise, right? If now we have to find the new path cost, right? Long new path cost will be what, right? The cost we have till now plus, right? One long multiply cost, right? So if we say if new path cost, right? If this is less than distance of what next, right? If it's less and new path cost, right? If it's less than equals to k, right? If it's greater than k, then this path will be invalid. So we need to update the distance. Distance will be new path cost, and we need to add it to the priority queue. Priority queue dot offer new state we need to add, right? That will be next, and new path cost, right? And if we don't find anything, then we return false. It means we haven't found any valid path. Okay. Seems good, I think. Now let's see, let's run it. So yeah, so it will be online dot length. Then we have more problems. Pair cannot be converted to list of pair. Cannot find symbol A dot V. Okay, so this will be only pair, right? Because adjacency dot current is a list. Then cannot infer type for priority queue. Queue state. Try. Let's see what do we have now. So we paired priority queue state PQ equals to new priority queue may not be. Seems correct. New. Do we not want any return inside this one? This comparator that we need to end. Okay, yeah, this passes the test case. Now let's see submit. Hope it works, but let's see if we got a wrong answer. Okay, so let's see this one now. Let's try to the edge is only 0 and 8. Online is true, true, true. Expected 7 and expected 8 and we return 7. Okay. So let's see where do we have this problem. We rewrite high, we do here and high equals to we update. So high becomes 0, 8, high becomes 8, low becomes 7. So 7 becomes valid. Okay, so I think this will be less than, right? Continue less than mid we don't want. But if it's equals to mid, we include it. Okay. Okay, right. So the condition, right, for 7 it becomes true, but for 8 it does not. So it will be less than equals to, I think. Yeah, let's use this test here to run it. Okay. Some small silly mistakes. Oh, we still have a long answer. So output is -1, expected is big number. What do we have wrong now? It's almost a few are left. So is this value less or what? So let's do is let's take it as. And what if we take long dot next value? I mean, this may be the path cost, right? If we do okay, if we run it was the or infinity is less actually. So okay, now we have TLE. So let's see TLE. I think we are missing the stale states in the Dijkstra's algorithm. So if we write if this passcode, right? So if p cost, right, not equals to what? The value that we have in Dijkstra's currently, we will continue it. So because we want to skip this one, right? Okay. Yeah. Okay, it works, yeah. So let's analyze the time complexity and other things now. So the approach is binary search, Dijkstra, very greedy, and the proposed approach was dynamic topological sort. That is fine. Time complexity is O of m log max cost log m. So you see this extra log m is we have due to binary search. Okay, yeah, thank you.